Galileo Galilei once remarked that the universe is a magnificent book composed in the language of mathematics. Today, we are going to explore a subject with the power to completely transform your perception of the world: the principle of time dilation. This concept dictates that the rate at which time flows for you is directly influenced by how fast you are moving. While this might seem like a premise from a science fiction story, it is a proven scientific fact, and astonishingly, it is affecting you at this very moment. Picture yourself standing on a station platform, looking at two perfectly synchronized clocks. One clock rests stationary on the platform before you, its second hand marking time with a steady rhythm. The other is secured inside a high-speed train that hurtles past you. As the train vanishes into the distance, a truly remarkable event takes place. The clock aboard the moving train begins to tick more slowly than its stationary counterpart. This isn't a mechanical glitch or some kind of error. It's because the very passage of time has decelerated for the object in motion. Let me be perfectly clear. This is not a theoretical idea or a piece of speculation. The effect is a tangible reality of our world, something we can measure and detect with precision instruments. You are about to enter the astounding universe of time dilation, where Albert Einstein's groundbreaking theories intersect with our daily lives in ways that appear paradoxical, yet are more real than the very ground you stand on. We will investigate how your velocity determines not just where you are in space, but also your unique position in time. We will examine why astronauts return from space younger than their twins who remained on our planet, why navigational satellites need their clocks constantly corrected, and how the cosmos has been manipulating time since its creation. What makes this subject so compelling is that time dilation isn't confined to spacecraft or orbiting technology. It has a direct impact on you, right now, even if the effects are too subtle to notice. With every step you take, every change in your speed, and every second you exist in Earth's gravitational field, you are experiencing this phenomenon. By the time we finish, you will not only understand the principles behind time dilation, but also see why this temporal structure was crucial for our universe to even exist. My goal is to guide you through one of modern science's most challenging concepts about reality itself. I will use relatable analogies, concrete examples, and mind-bending thought experiments that will question everything you thought you understood. We will begin with the fundamental ideas Einstein laid out more than a century ago, before moving on to material that can perplex even professional physicists. First, however, I want to show you just how significant this topic truly is. Back in 1971, an iconic experiment was carried out by the scientists Haffel and Keating. They synchronized 4 atomic clocks, the most accurate timekeeping instruments ever made, and flew them around the world on commercial aeroplanes. When the planes landed, these clocks displayed a different time than identical clocks that had stayed on the ground. The discrepancy was only a matter of nanoseconds, but it perfectly matched the predictions from Einstein's formulas. This experiment was far more than a clever scientific demonstration. It provided undeniable evidence that time is not some universal, unchanging constant. Instead, time is revealed to be flexible and elastic, its pace fundamentally tied to an object's motion and the strength of the gravitational forces acting upon it. The time on the airborne clocks had genuinely passed at a different rate compared to the time measured by the clocks on Earth's surface, a discovery that reshaped our understanding of the universe. Now, before we continue, it's essential to tackle the skepticism that naturally arises when you first encounter this idea. The immediate reaction is often disbelief, because how could time possibly slow down? Our intuition insists that time is just time, flowing identically for everyone, everywhere. The trouble is, this so-called common sense is frequently mistaken when confronted with the fundamental laws of reality. It's the same common sense that once told us the Earth was flat, that heavier things fall faster, and that light must be either a wave or a particle, but never both at once. Our intuitive understanding of the world is built from our daily lives, which are lived out at incredibly low speeds and in relatively weak gravitational fields. The reason time dilation feels so bizarre is that its effects in our everyday activities are so infinitesimally small, they go completely unnoticed. Yet, you should be certain that these effects are always there, operating continuously, and subtly altering the flow of time all around us. It's like trying to see the curvature of the Earth while standing in a field. The curve is real, but you need a much broader perspective to perceive it. To truly comprehend time dilation, we must first revisit what Einstein taught us about space and time themselves. The classical view treated space as a static arena, and time as a universal, ticking clock that measured events within it. Einstein's genius was in showing that this picture was deeply flawed. He proved that space and time are not separate, but are instead interwoven into a single, unified fabric known as Spacetime. Imagine this fabric as a vast, taut rubber sheet, where massive objects like stars and planets create dips and curves, and what we experience as gravity is merely the path objects take as they travel along these contours. It's crucial for you to grasp that the passage of time isn't uniform everywhere in our curved spacetime. Your position within a gravitational field directly affects its flow. So the deeper you venture into one, the more slowly time unfolds for you. Similarly, your velocity through space dictates your pace through time. The faster you travel, the more sluggishly time progresses for you. This leads us to a foundational pillar of physics, the speed of light, which travels at roughly 300 million meters per second in a vacuum. This velocity is an unchangeable constant for any observer, no matter how they are moving. While that might sound like a simple piece of trivia, it's the very reason time dilation is a physical necessity. To see why, consider how speeds normally combine. If you are in a car moving at 96 kilometers per hour and you toss a ball forward at 48 kilometers per hour, a bystander would measure the ball's speed at 144 kilometers per hour. Light, however, completely defies this classical addition of velocities. Imagine you're traveling at half the speed of light, and you turn on a flashlight. The beam doesn't shoot forward at 1.5 times light speed. Instead, it moves at the exact speed of light, no more and no less. This presents a baffling contradiction. How can light maintain the same speed irrespective of its source's movement? Albert Einstein's answer to this was world-changing. He proposed that space and time themselves must warp and bend, adjusting themselves to uphold the constancy of light's speed. Let me walk you through a thought experiment to make this clearer. Picture yourself on a train that is speeding along at 90% of the speed of light. When you shine a flashlight towards the front of the carriage, the beam appears to you to move at its normal, constant velocity. For an observer standing on the station platform, a question arises. What is the speed of that light beam from their viewpoint? According to everyday logic, the speeds should combine, resulting in a velocity far exceeding the universal speed limit, which we know cannot happen. The cosmos has an elegant solution. It slows down time for you on the train. To the person on the platform, it would seem as if your watch is ticking more slowly and your actions are in slow motion. For you, however, nothing would feel different. Everything would seem perfectly normal. The light from your flashlight maintains its constant speed precisely because your personal flow of time has decelerated just enough to make it so. This fundamental principle is the very core of time dilation. You should understand that this isn't a case of faulty clocks or some mechanical quirk. We are talking about the actual rate at which reality happens, time itself, altering based on your motion and the strength of gravity around you. This concept is not just a theoretical flight of fancy, as the effect has been confirmed repeatedly through highly precise measurements with atomic clocks, particle accelerators, and astronomical studies. The mathematics describing this phenomenon are both beautiful and exact. Einstein's formulas reveal that the effect of time dilation becomes more pronounced as your velocity nears the speed of light. At the speeds you encounter daily, the change is practically undetectable. Someone traveling at 96 kilometers per hour would experience a time difference on the scale of 10 to the minus 15th power. As you can see, it's only when speeds get extreme that the effect truly becomes significant. When you reach 90% of the speed of light, time slows by a factor of roughly 2.3, meaning just 1 second would pass for you for every 2.3 seconds that elapse for someone at rest. If you accelerate to 99% of light speed, that factor jumps to about 7. At 99.9%, it skyrockets to around 22. The closer you get to the ultimate speed limit, the more dramatically time stretches, approaching an infinite slowdown. This concept gives rise to some truly strange possibilities, like the famous twin paradox. Suppose one twin embarks on a journey to a far-off star at nearly the speed of light, leaving her sister behind on Earth. The traveling twin might experience the trip as lasting only a few months, but upon her return she would discover that decades have gone by for her earthbound sibling. She would now be significantly younger than her sister, a situation that seems paradoxical but is, in fact, a direct and logical outcome of time dilation. What's perhaps most incredible is that the spacefaring twin would have no sensation of time slowing. From her point of view, her watch would tick at a normal rate. Her body would age as it always does, and the laws of physics would operate just as she'd expect. The profound difference in their ages would only become evident at their reunion, when her personal timeline is directly contrasted with her sister's on Earth. This leads us to a central tenet of relativity. All motion is relative. You can only define movement in comparison to another object or reference frame. There is no absolute stationary point in the universe. This very principle extends to time dilation. If you were to fly past me at a tremendous speed, I would see your time running slow. But from your vantage point, you would see my time as the one that has decelerated. While this may sound like an impossible contradiction, it is not. The resolution lies in recognizing that we are both correct, but only within our individual frames of reference. The seeming paradox only emerges if you attempt to merge our two distinct experiences without considering the relativity of simultaneity. The idea that events happening at the same time for one observer may not be for another. Consider this. You actually encounter gravitational time dilation in your daily life. Every time you take an elevator, or even just walk up a flight of stairs, time literally passes a tiny bit faster on the top floors of a skyscraper compared to the ground floor. Although this difference is infinitesimally small, It is a genuine physical effect that we can measure with today's advanced instruments. At this point, you're probably asking how gravity fits into this picture of changing time. It's here that the full scope of Einstein's genius becomes apparent, as he recognized that the experience of gravity is fundamentally indistinguishable from acceleration. To understand this, just imagine you find yourself inside a closed elevator, completely unable to see outside. Under these circumstances, you are unable to distinguish between accelerating in an upward direction and remaining stationary within a gravitational field. It was this principle of equivalence that guided Einstein to the realization that gravity must have a direct impact on the passage of time. The more powerful the gravitational field is in any given area of space, the more significantly time decelerates there, leading to a truly remarkable insight. Time actually moves a tiny bit slower at sea level than it does on the peaks of mountains. While this disparity might appear trivial, amounting to roughly 10 nanoseconds per day for each meter of altitude, our modern atomic clocks are precise enough to measure even these infinitesimal shifts. The satellites for the Global Positioning System, or GPS, which orbit about 20,000 kilometers above the Earth, encounter time dilation from two sources: their incredible orbital velocity and their location in a comparatively weaker gravitational field. I want to delve into the GPS network because it stands as perhaps the most concrete and practically important illustration of time dilation in our everyday world. To deliver exceptionally accurate location information, GPS satellites require flawless time synchronization among themselves, as their entire function hinges on calculating the travel time of radio signals from multiple satellites to your device. The fascinating aspect here is that these satellites are moving at approximately 14,000 kilometers per hour and operate where Earth's gravity is considerably less potent. Consequently, they are subject to the undeniable effects of time dilation. The swift movement of the satellites results in their internal clocks ticking about 7 microseconds slower each day than clocks on the planet's surface. Counteracting this, however, is the weaker gravity at their orbital height, which causes their clocks to run faster by around 45 microseconds per day. When you combine these two effects, the net outcome is that the satellite clocks gain a total of about 38 microseconds daily when compared to clocks on Earth. This tiny fraction of a second might seem entirely inconsequential, but if left uncorrected, the resulting errors in the GPS network would accumulate to a navigational error of nearly 10 kilometers in a single day. To prevent this, engineers are constantly recalibrating the satellite clocks to compensate for these relativistic effects, without which the entire GPS system would become useless in a matter of hours. So, every time you use your phone for directions, you are directly benefiting from Einstein's theoretical contributions to relativity, a stunning example of how abstract physics concepts have found profoundly practical use in our lives. Yet, GPS is merely the first stop on our exploration of time dilation. The phenomenon has an influence on virtually everything, from the functioning of particle accelerators to the decay of cosmic rays entering our atmosphere. When high-energy particles from deep space collide with our atmosphere, they generate unstable secondary particles known as muons. These muons have an exceptionally brief existence, lasting only about 2.2 microseconds, which, in theory, is not nearly long enough for them to reach the Earth's surface before they decay. However, because they travel at speeds approaching that of light, time dilation extends their lifespan from our perspective just enough for them to complete their journey to the ground, where our instruments can detect them, providing direct proof of time dilation occurring in nature. What's particularly intriguing is that from the muon's own frame of reference, they don't experience any time dilation at all. They live for their standard lifespan and cover a normal distance. It is only from our stationary viewpoint that they appear to exist longer and travel farther, precisely because their time is passing more slowly relative to ours. These examples powerfully demonstrate that time dilation is not some theoretical oddity or a convenient tool for storytelling in science fiction. Instead, it is a foundational principle that governs the very fabric of our universe. Every elementary particle, every physical object, and indeed every living creature is subject to the effects of time dilation, dictated by its speed and its position within a gravitational field. The implications, however, grow even more profound. Time dilation doesn't just alter the ticking of mechanical clocks or the decay of particles. It also affects biological processes, the rate of chemical reactions, and even the pace of our own thoughts. If you were able to journey at a velocity nearing the speed of light, you wouldn't just age at a slower rate than stationary observers. Your cognitive functions would decelerate, your reaction times would lengthen, and your entire perception of life would shift to an entirely different temporal scale. This introduces deep philosophical questions about the nature of consciousness and the very meaning of our experience. If time itself is malleable, what does that imply about our perception of reality? And what further mysteries of time dilation has science yet to reveal? We are truly just at the outset of this incredible journey into the intricate labyrinth of time. In the next stages of our investigation, we will dissect the mathematical underpinnings of time dilation, explore the famous twin paradox in greater depth, and look at some of the most extreme instances of this phenomenon in the cosmos. We will venture toward black holes, where time all but grinds to a halt, and consider how time dilation influences the aging of stars, to assess if time travel, as we often imagine it, is even plausible. Before we proceed to those fascinating subjects, I urge you to reflect on what we have discussed, because time, this seemingly constant and integral part of our existence, is far more complex and strange than it initially appears. Time is not a rigid constant. Instead, its passage is fluid, relative, and completely contingent on movement and the forces of gravity. Each moment you live is molded by the principles of relativity, influences that are imperceptible to you yet constantly at play. So when you next look at a clock, understand that it isn't tracking some universal objective time. It's marking your own subjective journey through time, a passage uniquely defined by your velocity through the cosmos and your precise location within Earth's gravitational pull, revealing a universe far more intricate than our perceptions suggest. Let's venture further down this fascinating path, because grasping the true essence of time dilation will fundamentally alter how you perceive the cosmos. You'll begin to see that the idea of a universal present moment is an illusion. No single master clock governs the entire universe. Rather, each observer possesses a distinct temporal rhythm, a personal rate at which time unfolds, dictated by their unique trajectory through the fabric of four-dimensional spacetime. This realization leads to one of time dilation's most perplexing and counterintuitive outcomes: the issue of simultaneity. On a cosmic scale, the notion that two events can happen at the exact same instant in separate places becomes meaningless. Two occurrences that seem perfectly synchronized to one observer could happen at vastly different moments for another, who is traveling at a significant velocity relative to the first. This isn't an issue of imprecise instruments or signal delays. It is an intrinsic characteristic of the universe's temporal structure. The velocity of light represents far more than a simple speed barrier for physical objects. This fundamental constant is the very foundation upon which our reality is built, weaving together the dimensions of space and time. No object possessing mass can ever attain this final velocity, as doing so would necessitate an endless supply of energy. The most mind-bending implication, however, is that if an object could theoretically achieve the speed of light, its experience of time would come to a complete standstill. Allow me to demonstrate how these concepts would play out in the context of future interstellar travel. Consider Proxima Centauri, the star closest to us, situated about 4.2 light-years away. If you were on a starship moving at 1/10 the speed of light, observers on Earth would clock your journey at 42 years. At this velocity, time dilation is nearly insignificant, with a gamma factor of about 1.5, meaning the space traveler would age only 21 days less than people back home. Now, let's increase the velocity to 90% of light speed. For those watching from Earth, the trip would appear to last approximately 4 years and 8 months. But for you, the traveler, a gamma factor of 2.29 means that your personal experience of time would amount to only 2 years. Upon arriving at Proxima Centauri, you would find yourself 2.5 years younger than the peers you left behind on your home planet. Pushing the speed to 99% of the light barrier produces even more dramatic outcomes. While Earth's calendars mark the passage of about 4 years and 2.5 months, your ship's chronometer would have measured only 7 months. Imagine traveling to the closest star in under a year of your own subjective time, even as more than 4 years elapsed on Earth. Scenarios like this reveal extraordinary possibilities for exploring the cosmos. Let's imagine a far more ambitious voyage, a trip to the center of our galaxy, a distance of 26,000 light-years. From the vantage point of Earth, this journey, at speeds approaching that of light, would span 26 millennia. Yet, for you aboard the ship, the profound effects of time dilation could compress this epic trek into a mere handful of years, or perhaps even just a few months of your own perceived time. There is, however, a significant obstacle that cannot be overlooked. The energy demands for achieving such velocities escalate catastrophically as you near the light barrier. To reach 90% of light speed, the required energy would surpass conventional calculations by a multiple of 23. At 99%, that requirement grows 7 times larger, and to actually hit the speed of light would demand a limitless quantity of energy. This energy constraint isn't merely a technological hurdle. It's a basic principle of the universe. The equations that govern time dilation are fundamentally tied to the principle of mass-energy equivalence. As an object accelerates, its relativistic mass also increases, which in turn demands progressively more energy for any additional acceleration. This process establishes a natural cosmic speed limit, making it impossible for anything with mass to ever attain the velocity of light. Let's move from these extreme scenarios to examine time dilation in more everyday situations, as even a standard commercial flight produces detectable relativistic effects. On a typical transatlantic journey, flying at 10,500 meters and 800 kilometers per hour, time is altered by roughly 11 parts in 10 trillion. Over an 8-hour flight, this amounts to a difference of about 10 nanoseconds, a seemingly insignificant figure that can nevertheless be accurately recorded with atomic clocks. Consequently, pilots and flight attendants who spend their working lives airborne do age marginally slower than people on the surface. While the total difference over an entire career adds up to only a few microseconds, it represents a genuine and scientifically verified phenomenon. For an even more striking example, consider the International Space Station, or ISS, circling the Earth at an altitude of 400 kilometers and a velocity of 28,000 kilometers per hour. The ISS is subject to a combination of time dilation effects from both its high speed and its position in Earth's gravitational field. The influence of speed causes time to pass more slowly, whereas reduced gravity makes it pass more quickly. Consequently, for every year that passes, astronauts experience aging at a rate of about 1/10,000th of a second less than individuals on Earth. These instances highlight a critical truth. Time dilation isn't some abstract notion from theory or a mere plot device for fiction. It is a genuine, measurable phenomenon that impacts absolutely everything in our universe. And with each movement or change in acceleration you make, you are subject to its effects. Now, let's explore one of physics's most renowned thought experiments, the twin paradox. This particular scenario serves as a brilliant illustration of the seeming contradictions within time dilation and how they are ultimately reconciled. Picture two identical twins, Anna and Victor. While Anna remains on our planet, Victor embarks on a journey to a far-off star, traveling at 90% of the speed of light. From the viewpoint on Earth, his entire round trip lasts 10 years. However, upon Victor's return, the effects of time dilation mean he has only aged 4 years and 4 months, while his sister Anna has experienced the full decade, making Victor 5 years and 8 months younger. Here, however, we encounter a fascinating dilemma. From Victor's vantage point during his voyage, it is Earth and Anna that are moving away at 90% of light speed. So shouldn't he perceive her clock as running slower? The key to resolving this puzzle is found in the asymmetry of their experiences. Anna's existence is confined to a single inertial frame of reference, but Victor's journey requires him to accelerate at the beginning, decelerate as he approaches the star, accelerate once more for the trip home, and finally decelerate to land. These periods of acceleration are what shatter the symmetry and solve the paradox. During the long stretches of constant speed travel, both twins would indeed observe the other's clock ticking more slowly. Yet it's during his phases of acceleration and deceleration that Victor would see Anna's clock rapidly speed up, a process that more than compensates for the time it appeared to lose. As a result, Victor genuinely ages less than Anna. The mathematics of relativity shows that the solution to the paradox hinges not just on relative speed, but on the complete history of an object's motion. The twin who undergoes acceleration is the one who ages more slowly, a fact that links time dilation to the principle of equivalence, the concept that acceleration and gravity are fundamentally interconnected. Following that connection to gravity, let's delve into gravitational time dilation. Albert Einstein's general theory of relativity posits that the stronger the gravitational field, the slower time proceeds. While this effect is separate from the time dilation caused by velocity, the two are intimately related, as both originate from the single underlying principle of spacetime curvature. The mathematics describing this is remarkably elegant. Time's pace is dictated by gravitational potential. Here on Earth's surface, the effect is almost imperceptible, amounting to about 1 part in 10 billion for each meter you go up. Near incredibly massive objects like neutron stars, however, the phenomenon becomes truly extraordinary. Consider a neutron star with double the mass of our Sun but crushed into a sphere merely 20 kilometers across. Its surface gravity is 100 billion times more powerful than Earth's, causing time there to flow roughly 30% more slowly than it does in deep space. We can actually observe this effect in the X-ray emissions from these stars. As material crashes onto a neutron star's surface, the intense gravitational compression heats it until it radiates X-rays. Because of the powerful gravitational time dilation, these X-rays are redshifted, meaning their frequency is lowered. By carefully measuring this redshift, astronomers are able to calculate the mass and radius of the neutron stars they study. Yet even these dense objects are dwarfed by black holes. As you draw closer to a black hole's event horizon, the point of no return, gravitational time dilation escalates to extreme levels. From the perspective of a distant observer, time at the event horizon itself would appear to stop completely, stretching into infinity. This leads to a baffling situation where, from the universe's point of view, nothing ever truly crosses the event horizon. Any object falling in would seem to slow down, freeze at the edge, and then fade away as its light redshifts into obscurity. For an observer who is actually falling into the black hole, however, the experience is completely different. According to their own clock, they pass through the event horizon in a finite amount of time, with no inkling that they appear suspended in time to the rest of us. This illustrates one of the most incredible discoveries of general relativity. The nature of a single event in time is entirely dependent on your frame of reference. Understanding these extreme instances of time dilation has real-world importance for our comprehension of the cosmos. Astronomers studying matter plunging into black holes must incorporate these effects to correctly analyze their data. The behavior of accretion disks, the spiraling whirlpools of superheated gas surrounding black holes, is governed by physical laws that have been profoundly altered by this extreme time dilation. This brings us back to Earth and the practical technologies that rely on these principles. The most common example of time dilation impacting our technology is the Global Positioning System, or GPS. The satellites for this system orbit at an altitude of approximately 20,200 kilometers, where Earth's gravity is significantly weaker. This weaker gravity causes their internal clocks to run faster than clocks on the ground, by about 45 microseconds each day. At the same time, these satellites are moving at roughly 14,000 kilometers per hour, and this high velocity slows their clocks down by about 7 microseconds per day. For your GPS to function, both of these relativistic effects must be precisely calculated and corrected for. The cumulative effect is that satellite clocks run ahead of their terrestrial counterparts by approximately 38 microseconds every single day. While this may sound like an insignificant discrepancy, the Global Positioning System, or GPS, functions on a standard of nanosecond precision. An uncorrected timing error of 38 microseconds would accumulate into a positioning mistake of about 10 kilometers, rendering the entire system utterly useless in just a matter of hours. To counteract this, the engineers who designed the GPS network brilliantly built these relativistic effects directly into the system's architecture. Before being sent into orbit, the clocks on each satellite are intentionally calibrated to run a fraction slower than normal. Once they are in space and subject to the full force of relativity, they synchronize perfectly with time on Earth. a remarkable illustration of how purely abstract physics concepts become indispensable for our practical technologies. Every time you use a navigation app on your phone, you are directly benefiting from the precision of Einstein's calculations. GPS is far from the only example of time dilation's influence on modern science. Particle accelerators, like the renowned Large Hadron Collider, or LHC, depend entirely on this principle to operate. When particles are propelled to speeds approaching that of light, they undergo extreme time dilation from our point of view. Consequently, particles that would typically disintegrate in microseconds survive for much longer, giving them enough time to circle the 27-kilometer ring multiple times before they are made to collide. Without this extension of their lifespan due to time dilation, most particles would decay long before ever reaching the collision detectors. Therefore, every breakthrough in particle physics, from pinpointing the Higgs boson to discovering new subatomic particles, is fundamentally reliant on our comprehension of how time dilation alters the existence of these high-velocity objects. This very same principle is at work in the detection of cosmic rays that constantly bombard our planet from space. When particles traveling at immense energies from deep space strike Earth's atmosphere, they generate showers of secondary particles, which include muons. These muons possess an incredibly brief lifespan of about 2.2 microseconds. According to classical physics, muons traveling at their typical speeds should decay well before they could ever reach the ground. However, thanks to time dilation, their existence is prolonged just enough for them to be registered by our ground-based detectors, allowing scientists to study the universe's most energetic phenomena. These concrete applications of time dilation truly showcase the profound nature of scientific discovery. Theories that might initially appear abstract and disconnected from our daily experience frequently lead to practical innovations that completely reshape our world. Einstein's theories of relativity began as pure intellectual exercises, yet they now form the bedrock of technologies you and I use every day. This powerful link between theory and practice highlights the incredible utility of mathematical physics. The very same equations that describe the warping of time near a black hole are used to calibrate the clocks in GPS satellites, and the identical principles that explain the behavior of cosmic rays also govern the operation of particle accelerators. It reveals that the universe functions according to consistent mathematical laws, irrespective of the scale or situation in which they manifest. This relativity of time, however, invites us to ponder much deeper questions about the fundamental fabric of reality. If time truly flows at different rates for different observers, what are the implications for our very concept of existence? Could there be aspects of reality that lie beyond the relativistic nature of time? And how can we reconcile our subjective human perception of time with the objective, measurable reality of time dilation? These inquiries lead us into the deepest puzzles of modern physics, touching upon the relationship between time and consciousness, the nature of causality, and the theoretical possibility of time travel. But for now, understand that as we delve into this temporal labyrinth, everything we've discussed is not mere speculation, but a tangible, observable fact. Time dilation is happening constantly all around us. Every satellite in orbit, every cosmic ray striking the atmosphere, and every particle within an accelerator serves as a testament that our intuitive sense of time is incomplete. The universe is far more intricate and awe-inspiring than we can possibly imagine, and time dilation is just one of its many incredible features. In our future explorations, we will venture into even more extreme domains of space-time, where the effects of time dilation become so profound they challenge our most basic assumptions about reality. Deep within the cosmos, something even more bizarre is waiting for us. Black holes. These cosmic behemoths don't merely bend light and warp space. They twist time itself into forms we can barely comprehend. In the vicinity of a black hole, time doesn't just slow down, it grinds to a near halt. Let me try to paint a clear picture of what this experience would be like. Imagine you are safely watching a friend journey toward a black hole. As they approach the point of no return, the event horizon, something extraordinary occurs from your perspective. You would observe their movements becoming progressively sluggish, their descent slowing until, eventually, they appear to freeze completely, suspended at the edge of the horizon. Their image would simultaneously grow dimmer and shift toward the red end of the spectrum as time dilation stretched towards infinity, until they faded from sight entirely. Here is the truly mind-bending part. From your friend's perspective, none of this is happening. They would cross the event horizon in what feels like a perfectly normal span of time, entirely oblivious to the fact that, to the rest of the universe, they are frozen for eternity. They would continue to experience the ordinary passage of time all the way until they reached the singularity at the black hole's center. This gives us two radically different yet equally valid experiences of the same event, a paradox at the heart of reality itself. This is precisely where Einstein's ideas lead us into territory that feels more philosophical than physical, prompting us to question what it truly means for different observers to perceive time in their own way. Without a universal cosmic clock, what is it that defines the present moment? The answer is at once straightforward and profound. There is no single, universal present. Each of us carries our own personal timescale, a unique slice of the now that is molded by our specific journey through spacetime. Just consider the implications of this. As you absorb these words, someone traveling at an immense velocity relative to Earth is experiencing this very moment differently. An astronaut on the International Space Station, for example, exists in a slightly altered present. A difference measured in tiny fractions of a second, but one that is entirely real. This realization leads to one of the most perplexing discoveries in modern physics: the nature of causality. The intuitive idea that causes must always precede their effects becomes tangled in a relativistic framework. When two separate events appear to happen simultaneously for one person, yet another observer witnesses them occurring at different times, whose perception is actually correct? The key to unraveling this puzzle lies in determining whether these events could influence one another via signals traveling at the ultimate cosmic speed limit: the speed of light. For instance, imagine two powerful supernovas exploding on opposite sides of our galaxy. From your vantage point, they might seem perfectly synchronized, like a cosmic fireworks show choreographed to a single beat. However, for an observer hurtling through space at incredible speed, one explosion could precede the other by many years. And astonishingly, both viewpoints are considered absolutely valid. So, how does the universe maintain the logical flow of cause and effect under these strange conditions? Nature has an elegant solution. Causal relationships can only exist between events that fall within each other's light cones. This concept maps out a beautiful geometric structure within spacetime, with every event in the universe residing at the center of its own light cone, which clearly demarcates the boundaries of its influence. The past light cone contains all events that could have possibly affected the present moment. while the future light cone encompasses all events that the present moment could potentially affect. Anything outside of these cones exists in a mysterious region where simultaneity is truly relative, and the sequence of events is dictated by the observer's motion. Now, let's shift our perspective from these vast cosmic scales to something far more immediate: the device in your pocket. Your smartphone makes use of time dilation corrections in ways that most users would never imagine. This isn't just about global positioning systems, or GPS, but about how the device functions at a fundamental level, where relativistic effects are critical in the quantum realm. Deep inside your phone's processor, electrons zip around at a significant fraction of the speed of light, and at such velocities, these phenomena are essential for the entire system to work. Modern semiconductor technology must factor in these effects during the design phase, otherwise your device would simply not operate correctly. Every time you send a text or make a call, you are unknowingly depending on an engineer's deep understanding of how time dilation modifies the behavior of electrons in silicon. Similar principles find their application in medical particle accelerators. When oncologists utilize proton therapy to fight cancerous tumors, they accelerate protons to an incredible 60% of the speed of light. At such unimaginable speeds, time dilation starts to have a major impact on how these protons interact with living tissue. Medical physicists are required to account for these relativistic effects with meticulous care to guarantee the most precise targeting of afflicted areas while minimizing harm to healthy cells. It is quite something to consider that cancer treatment literally hinges on our grasp of how time flows at the subatomic level. Even more astonishing is how time dilation shapes the most fundamental processes of life on our planet. The radioactive decay of elements, which is what powers Earth's molten core and propels the movement of tectonic plates, follows the laws of quantum mechanics. However, the rate of this decay is influenced by gravitational time dilation. Deep within the Earth's crust, where the gravitational field is substantially stronger, radioactive elements decay at a slightly different pace compared to those on the surface. This creates a remarkable feedback loop. Our planet's geological structure alters the passage of time, and time, in turn, impacts geological activity. But the real wonder is still ahead, as DNA replication, the foundational process for all life, happens at a molecular scale where quantum phenomena become all-important. The very enzymes that replicate your genetic code function based on the principles of quantum mechanics, which themselves are subject to the effects of time dilation. This means that every cellular division, each beat of your heart, and all the thoughts that fire in your brain are subtly governed by the relativistic nature of time. You are, in a very real sense, constructed from processes that follow Einstein's laws. It's important to realize this doesn't mean you can feel time dilation in your everyday experience. The effects are far too minuscule to be perceived directly. Nonetheless, they are undeniably real and are woven into the deepest fabric of our existence, making you a relativistic creature living in a relativistic cosmos, whether your senses can detect it or not. Now, let's consider what would happen if we could push time dilation to its theoretical maximum. Suppose humanity develops a starship capable of reaching 99.9% of the speed of light. At this velocity, the time dilation factor would be roughly 22. For every single year that passes for the crew on their voyage, 22 years would elapse back on Earth. Consequently, a trip to the center of our Milky Way galaxy, a journey that would typically take 26,000 years, could be completed in just 1,000 to 1,200 years from the traveler's point of view. That's a staggering reduction in travel duration. But we are still far from the ultimate limit. If we increase the velocity to 99.99% of light speed, the time dilation factor jumps to approximately 71. For the spacefarer, that epic galactic journey would now only take about 370 years. Pushing even further, to 99.999%, boosts the factor to around 224. The voyage's duration shrinks to a mere 116 years for the traveler, even as over 26,000 years unfold on our home planet. These astonishing figures highlight a profound truth about the universe's design. There is theoretically no upper boundary to time dilation, provided you never actually reach the speed of light. With enough energy and groundbreaking technology, it's conceivable that an astronaut could journey to distant galaxies and return to Earth within a normal human lifespan, while millions of years have passed for everyone else. Such a reality presents incredible prospects for the future of space exploration. The concept of generation ships, enormous vessels built for voyages lasting many centuries, could become obsolete if humanity masters this level of time manipulation. A small team of explorers might chart the entire galaxy and come back home in their own lifetime, only to discover a world transformed beyond recognition. This possibility raises fundamental questions about human civilization and experience. If you were given the opportunity to travel to another galaxy, subjectively aging only a few decades but returning to an Earth millions of years in the future, what would that do to your bond with humanity? Would you still feel human in any significant way? Or would you become an entirely new kind of being? A temporal exile from a forgotten age, carrying memories of a world that has long since vanished. These considerations move us well beyond the scope of physics and into the domains of philosophy and existential thought. Time dilation isn't just something that affects clocks and particles. It touches upon the very definition of existence, our sense of identity, and the continuity of consciousness. If time itself is relative, then the human experience must be as well. Your entire existence, from your birth to your death, represents just one narrative among an infinite number of equally valid stories unfolding across the space-time continuum. Let's bring our focus back to the present and examine how time dilation shapes our understanding of cosmic history. When our telescopes gaze at far-off galaxies, we are essentially looking back in time, seeing them as they were billions of years ago. The light from these cosmic islands has journeyed through space-time regions with different gravitational forces, and therefore different rates of time flow. This reveals that the universe's history is not a straight chronological line, but a complex tapestry of events happening at different paces throughout space-time, making every deep space observation a practical lesson in relativity. For instance, the cosmic microwave background radiation, which is the faint afterglow of the Big Bang, holds precious data about the universe's earliest moments. However, this information has been filtered through billions of years of time dilation as it traveled across the expanding cosmos. To accurately interpret their findings, cosmologists studying the universe's infancy must meticulously factor in these relativistic effects. Even the redshift of distant galaxies is a product not only of spatial expansion, but also of the time dilation caused by the matter and energy the light encountered on its long trek to us. For instance, the cosmic microwave background radiation, which is the faint afterglow of the Big Bang, holds precious data about the universe's earliest moments. However, This information has been filtered through billions of years of time dilation as it traveled across the expanding cosmos. To accurately interpret their findings, cosmologists studying the universe's infancy must meticulously factor in these relativistic effects. Even the redshift of distant galaxies is a product not only of spatial expansion, but also of the time dilation caused by the matter and energy the light encountered on its long trek to us. For instance, the cosmic microwave background radiation, which is the faint afterglow of the Big Bang, holds precious data about the universe's earliest moments. However, this information has been filtered through billions of years of time dilation as it traveled across the expanding cosmos. To accurately interpret their findings, cosmologists studying the universe's infancy must meticulously factor in these relativistic effects. Even the redshift of distant galaxies is a product not only of spatial expansion, but also of the time dilation caused by the matter and energy the light encountered on its long trek to us. A fascinating paradox arises from this. Our universe has a definite age of approximately 13.8 billion years, yet the passage of time since the Big Bang has not been uniform everywhere. Near incredibly massive objects like black holes, considerably less time has gone by. Conversely, in the great voids between galactic clusters where gravity is weak, much more time has elapsed. The universe, it turns out, is expanding not just through space, but also through time, a concept that, while sounding strange, is a documented scientific fact. Here is an idea that can genuinely alter your perception of everything. The expansion of the universe itself is a source of time dilation. As space stretches, it effectively pulls time along with it. This means the speed at which time flows is determined not just by gravity and velocity, but also by the very rate at which the cosmos is expanding. Your experience of time is tied to the grand, ongoing evolution of the entire universe. You live in a universe where the fabric of time is actively being stretched by the expansion of space itself, a fact that has deep consequences for its ultimate destiny. Should this expansion continue to speed up, driven by the enigmatic force of dark energy, the distorting effects on time will grow ever more significant. Far into the future, as the cosmos becomes a cold and desolate void, the very passage of time could become unrecognizable, flowing in a manner completely alien to our current experience, and culminating in a heat death that signifies the end of time as a concept. An even more fascinating scenario to consider is what might occur if the universe's expansion were to halt and reverse into a great contraction. In this big crunch, the effects of time dilation would flip, causing areas where time once moved slowly to experience an intense temporal compression. The cosmos would not merely shrink in space, it would undergo a collapse in time, with this final moment arriving unevenly across different cosmic regions. These grand cosmic outcomes of time dilation unveil a profound link between the universe's largest structures and the tiniest realm of quantum mechanics. You see, the very same mathematical rules that dictate how time behaves near a black hole are also the ones that shape the universe's evolution across eons. It's through the equations of general relativity that the actions of single particles are tied to the destiny of the entire cosmos, demonstrating an astonishing coherence in the laws of nature. This line of thinking leads us directly to one of the most dynamic fields in contemporary physics, the pursuit of a unified theory of quantum gravity, While general relativity describes time dilation as a classical phenomenon, at the most fundamental levels, the strange rules of quantum mechanics reign supreme. Understanding how time dilation functions when these quantum effects become dominant remains one of the most profound and unanswered questions in all of science. Certain hypotheses propose that time itself is quantized, made up of indivisible moments known as Planck time, which would imply a fundamental limit to how much time can be dilated. Alternatively, other theories suggest that time isn't a fundamental aspect of reality at all, but rather an emergent quality arising from deeper quantum processes. Pondering these ideas takes you to the absolute edge of human comprehension, a place where physics and mathematics merge with philosophy and the nature of existence. Now, I'd like to bring us back to more tangible considerations and explore how time dilation could impact the search for life beyond Earth. If alien societies are out there, their experience of time would be unique to their specific location and velocity within the galaxy. For instance, a civilization on a world orbiting tightly around a massive star would be subject to time dilation so extreme that it could profoundly shape its entire evolutionary and developmental trajectory. Just picture trying to establish contact with such a civilization. Any radio transmission you sent from Earth could arrive at their planet highly compressed because of relativistic distortions. A message that you perceive as a normal conversation might sound to them like speech sped up to an unintelligible rate. In turn, their replies would seem agonizingly sluggish from your point of view, presenting a fundamental obstacle to any meaningful interstellar dialogue. This entire problem introduces captivating questions regarding the essence of intelligence and consciousness within a relativistic cosmos. If time dilation slows down cognitive functions, does the quality of the thoughts themselves change? Could a society subjected to powerful time dilation think at a slower pace, yet with greater depth and thoroughness? It's even possible they might evolve completely different modes of consciousness, uniquely suited to their altered temporal framework. These inquiries gain even more weight when you introduce the potential of artificial intelligence. An AI running on a starship moving close to the speed of light would be affected by time dilation just like any physical object. To an outside observer, its processing speed would appear to be slowed down, yet from within its own reference frame, its thoughts and calculations would proceed at a perfectly normal rate. This concept gives rise to the possibility of what you might call temporal artificial intelligence, systems engineered to operate across varied time scales. An AI could be designed to treat time dilation not as a constraint, but as a strategic asset, allowing it to undertake missions of such long duration that they would be impossible for biological beings. These AIs could then act as translators between different temporal realities, bridging the fast-paced time of a planet-bound civilization and the slow, stretched-out time of a journey between the stars. Of course, these technological prospects also bring forth complex ethical questions about consciousness and identity in a universe governed by relativity. If an AI's experience of time is dilated, should you grant it the same moral standing as a biological mind? Are there fundamental rights and duties that remain constant, regardless of the relativistic flow of time? These issues will become increasingly urgent as our AI systems become more sophisticated and our reach extends deeper into the cosmos, forcing us to reevaluate our core ideas of mind, consciousness, and ethics within this new physical context. Finally, I want to touch on one of the most debated yet alluring facets of time dilation: its link to the concept of time travel. Although journeying into the past is largely theoretical and perhaps physically impossible, Time dilation offers a scientifically sound method for traveling into the future. Any trip you take at very high speeds is, in effect, a voyage forward in time, permitting travelers to advance further into the future than those they left behind. This opens up remarkable possibilities for space exploration, where a mission to a faraway star could also be a trip that allows astronauts to see what becomes of humanity over hundreds or even thousands of years. Imagine astronauts embarking on a mission to a distant star. Upon their return, they could discover an Earth that has been completely reshaped by immense technological and societal progress. This possibility, however, opens the door to paradoxes and ethical questions on an unprecedented scale. If you possessed the power to travel into the future via time dilation, would you accept the burden of warning humanity about impending calamities? Could you even alter events that, from your vantage point, have already transpired? The very fabric of causality in space-time grows incredibly intricate when time dilation permits such profound temporal jumps, raising fundamental questions about free will, destiny, and our capacity to change the future. Some physicists theorize that within extreme gravitational fields, it might be possible to form closed, time-like curves, paths in space-time that circle back to their own temporal origin. Such a phenomenon would constitute genuine time travel, allowing for movement not just forward, but also into the past. While these concepts remain deeply speculative, they vividly demonstrate how our evolving comprehension of time dilation is continually pushing the limits of what we imagine is achievable. The mathematical equations of general relativity do not forbid the existence of closed time-like curves, yet they demand exotic conditions that may not be present in our universe. While rotating black holes or cosmic strings could theoretically generate the required space-time curvature, the immense energy demands and stability problems render such possibilities exceptionally improbable. Nevertheless, the sheer fact that these outcomes are permitted by the equations highlights the profound gaps in our current understanding of time and causality. As we explore these speculative frontiers, it becomes clear that time dilation is interwoven with the deepest enigmas in physics, including the essence of time itself, the architecture of space-time, and the connection between quantum mechanics and gravity. All these essential inquiries help clarify why the passage of time is perceived differently by various observers. Perhaps the most significant consequence of time dilation lies in what it suggests about the nature of existence. It reveals that we are not simply detached observers in the cosmos. Instead, we are active participants woven into its temporal framework. Each moment of our lives helps to form the complex web of causal connections that constitutes reality, with our individual timelines serving as threads in the magnificent tapestry of space-time, each one distinct, yet fundamentally connected to all others. This viewpoint radically alters our conception of life, death, and the very meaning of our existence. If time is relative, then our being within it is also relative. The moment you were born, the moment you will die, and your entire life's journey represent just one of countless possible trajectories through space-time. From a cosmic standpoint, your whole life exists concurrently with the Big Bang, the birth of the first stars, and the ultimate destiny of the universe. This perspective does not devalue the importance of your life. On the contrary, it greatly amplifies it. You are far more than a fleeting configuration of atoms and energy. You are an enduring feature of space-time itself. Your existence has etched a singular path through the fabric of reality, a trajectory that will forever be real and forever be integrated into the structure of the cosmos. Time dilation imparts a crucial lesson. The universe is not merely more bizarre than we imagine. It is more bizarre than we are capable of imagining. From the vastest clusters of galaxies down to the tiniest subatomic particles, every component of reality follows principles that defy our daily intuition. We are compelled to reevaluate what it means to exist in this extraordinary relativistic universe, a wondrous domain where gravity and velocity dictate the flow of time, and the idea of simultaneity loses all absolute significance. As we delve into these enigmatic mechanics of the temporal continuum, we stand on the verge of discovering even more astonishing phenomena and awe-inspiring possibilities. Our journey ahead includes an immersion into the quantum realm, where time itself might possess a discrete, granular structure. We will also investigate the latest findings on black holes, where the curvature of time is pushed to its absolute extreme, and explore revolutionary theories that might unify time with the other fundamental forces of nature. Before we proceed, however, it is vital to internalize this reality. The warping of time is not some abstract concept confined to physics textbooks. It is a foundational principle of the universe's design that shapes every facet of existence, from the navigation systems in your phone and the cosmic rays bombarding our world, to the nuclear fusion inside the sun and the quantum processes firing in your own brain. Every one of these is subject to the relativistic laws of time. Consider this the next time you look at a clock. What it displays is not some universal, abstract time, but rather your own personal experience of time's passage, defined by your motion through space and your location within Earth's gravitational field. You inhabit your own distinct temporal reality, subtly different from that of everyone else, yet intimately bound to the immense network of the space-time continuum that encompasses all things. As we get ready to probe these mysteries more deeply, remember that we are doing more than just analyzing theoretical models. We are uncovering the fundamental architecture of reality itself, the invisible framework that underpins everything we know and can imagine. The distortion of time is the very key that will unlock the most profound secrets of the cosmos, and we are only just beginning to grasp the revelations these secrets might hold. Our expedition through the labyrinths of time is just getting started. Every new insight propels us away from our comfortable, everyday intuitions and draws us toward the magnificent, beautiful, and profoundly strange reality of our cosmos. The distortion of time's flow involves much more than merely the slowing of clocks or variations in how astronauts age. It touches upon the fundamental nature of being in a universe where time is just as fluid and pliable as the space we navigate. In the discussion to follow, we will take these ideas to their logical extremes, examining scenarios where the distortion of time grows so severe that it defies our deepest assumptions about existence and reality. We will delve into the event horizons of black holes, where time as we know it effectively stops, and look at the most current theories regarding the quantum behavior of temporal phenomena. Our journey down this rabbit hole is only getting deeper, with the revelations ahead poised to dwarf everything we have learned so far. It is in this context that the distortion of time unveils its most mind-bending qualities. While we have discussed scenarios involving incredible speeds and colossal celestial bodies, the truth is that the warping of time is affecting you at this exact moment. A mere century ago, such a notion would have been dismissed as pure fantasy. Your head is aging at a faster rate than your feet. Although the discrepancy is infinitesimal, amounting to roughly 90 billionths of a second across an average human lifespan. Our modern atomic clocks are sensitive enough to measure this tiny variance. The phenomenon is caused by the variation in the gravitational field between your head and your feet. A height difference of only 2 meters is sufficient to produce a detectable distortion in the passage of time. This is not simply a piece of trivia. It serves as a powerful reminder that you live within a continuous gradient of time's flow, where each centimeter in elevation brings with it a subtly altered temporal rate. Your own body functions as a constant experiment in relativity, extended through different time frames from the crown of your head to the bottoms of your feet. Even the blood coursing through your veins encounters innumerable microscopic shifts in time, depending on its location in your brain or your heart. Now, let's explore an idea that will completely revolutionize how you think about time's nature. What if I proposed that the distortion of time's flow doesn't just alter the pace at which moments unfold, but actually dictates whether 2 events happen concurrently? This question leads us directly to the relativity of simultaneity, which stands as one of the most paradigm-shifting discoveries in the entire history of physics. Picture yourself on a station platform as a train speeds by at a substantial portion of the speed of light. On board that train, an individual simultaneously drops a ball and activates a flashlight. For you, the observer on the platform, these 2 actions are not simultaneous. You might perceive the ball falling before the flashlight turns on, or the reverse, all depending on the train's speed and direction. Both occurrences are perfectly real, yet their order is dictated entirely by your motion relative to the train. This outcome is not a result of some technical limitation in our measurements or a flaw in our observation. It is an inherent characteristic of the universe's fabric. There is no singular, universal now that applies everywhere. No master cosmic clock is ticking away in the vastness of space. The very concept of the present moment is intensely personal, uniquely private, and wholly contingent on your specific trajectory through space-time. Think about what this implies for the very essence of reality. As you process these words in what you perceive as your present, a civilization on a distant planet might be witnessing an event they see as happening at the exact same time. However, for a different observer, in another frame of reference, that same event could have taken place 1,000,000 years in the past, or may not occur for another 1,000,000 years. Astonishingly, all 3 of these viewpoints are equally legitimate, equally factual, and equally correct. This realization brings us to the concept known among physicists as the block universe. If the simultaneity of events is relative, it follows that from a particular vantage point, the past, the present, and the future all coexist. Your birth, your eventual death, and every single moment you experience are all equally real, just located at different coordinates within the space-time continuum. The universe, in this view, is less like a movie being played out 1 frame at a time and more like a vast sculpture, with every moment eternally preserved in the amber of space-time. This viewpoint fundamentally changes our perspective on concepts like free will, destiny, and the very meaning of existence. If every moment already exists, are we genuinely making choices, or are we merely traversing predetermined paths that are already woven into the structure of space-time? Such questions push us beyond the boundaries of physics and into the domain of philosophy, yet they stem directly from our scientific grasp of time's distortion and the relativity of simultaneity. Let's ground this in a more tangible example. The Large Hadron Collider, or LHC, that incredible feat of engineering buried under the border of Switzerland and France, is quite literally a time machine. I do not mean this in the way of science fiction, but in the most direct sense possible, as it engineers conditions that produce extreme time distortion. When protons are accelerated to 99.991% of the speed of light, they are subjected to a time warping factor exceeding 7,000. From our stationary viewpoint, these protons circle the 27-kilometer ring approximately 11,000 times every second. Yet, from the proton's own reference frame, the time it takes to complete that journey is significantly longer. In their temporal reality, the entire accelerator structure contracts from 27 kilometers down to a length of only about 4 meters. They slam into other protons within their own dimension of time, completely oblivious to our perception of them as objects moving near the ultimate cosmic speed limit. Every single collision that occurs within the LHC provides a real-world demonstration of time distortion at work. The exotic particles created in these impacts have incredibly brief lifespans, often lasting for just minuscule fractions of a second. However, the warping of time effectively prolongs their existence just long enough for our sophisticated detectors to capture and record them. Particle physics would be utterly inconceivable without the theory of relativity. For instance, the discovery of the Higgs boson, the particle responsible for imparting mass to all others, was only possible because the warping of time allowed it to exist just long enough for detection. This phenomenon is intricately linked to the very essence of what mass is. Einstein's renowned equation, E=mc², is profoundly connected to the distortion of time. As any object with mass accelerates toward the speed of light, its relativistic mass grows, demanding progressively more energy for any further increase in speed. This isn't merely a mathematical abstraction. It is the physical principle that establishes the speed of light as the ultimate velocity limit in the universe. Now, this is where the implications become truly fascinating. Massless particles, like photons, perpetually travel at the speed of light, and as a result, they undergo what can be described as infinite time warping. From the perspective of a photon, its entire journey unfolds with no time passing at all. A photon generated in the sun's core experiences its 8-minute voyage to Earth as an instantaneous event, created and absorbed in a single moment, irrespective of the vast distance it crosses. This leads to a stunning paradox. Light, which seems to connect every corner of the universe instantly from its own frame of reference, actually operates outside of time as you and I perceive it. Every photon transports information from its point of origin to its destination without experiencing any temporal duration. The light from a distant star that is just now reaching your eyes may have been emitted billions of years ago, but for that photon, it remains in the very instant of its creation. This provides a new framework for understanding the universe's structure, where space and time are not distinct, but are woven together into a single fabric called spacetime. Light, moving at the very speed that unifies space and time, inhabits a domain where this distinction dissolves. Photons act as the messengers of spacetime, ferrying information across immense cosmic expanses while being immune to the passage of time. This brings us to one of the most dynamic fields in modern physics, the quest for gravitational waves. These disturbances in the fabric of spacetime propagate at the speed of light, carrying with them information about the universe's most violent occurrences. When two black holes merge, for example, they produce gravitational waves that expand outward, taking energy and angular momentum with them. Most remarkably, these waves are literal ripples in time itself, causing the flow of time here on Earth to subtly accelerate and decelerate by infinitesimal amounts as they pass by. Instruments like the LIGO detectors, which made the first successful discovery of gravitational waves, are engineered to measure these minuscule effects of time warping. As a gravitational wave moves through one of the detectors, it not only stretches and compresses space, but also does the same to time. The laser beams inside the device travel slightly different paths, not just due to spatial distortion, but because time itself is flowing at marginally different rates in separate parts of the apparatus. We are, in effect, listening to the symphony of the cosmos by measuring the very rhythm of time. This pursuit extends into what sounds like science fiction, but is, in fact, the frontier of physics research. Scientists are currently designing advanced gravitational wave detectors with the potential to sense time-warping effects caused by dark matter. If dark matter particles interact through gravity, they ought to produce minute fluctuations in the rate of time's flow, which could be registered by instruments of sufficient sensitivity. Such a discovery would fundamentally alter our comprehension of the universe's architecture, as dark matter constitutes about 27% of the cosmos's mass energy, yet remains undetected. To speculate even further, certain theories propose a deep connection between the warping of time and the very expansion of the universe. According to this idea, as space expands, it effectively drags time with it, leading to a kind of temporal stretching that influences how we perceive the universe's age and scale. This could potentially resolve some of modern cosmology's greatest puzzles, including the mystery of why the universe's expansion is accelerating. This interplay between time distortion and cosmic expansion prompts profound questions about the nature of time on the grandest scales imaginable. If the universe is growing, is time also expanding along with it? Are we inhabitants of a cosmos where both space and time are continuously increasing? Inquiries like these push our understanding of reality to its absolute limits. Imagine the implications of this for the universe's ultimate destiny. If the effects of time warping intensify as the universe continues to expand, then in the far future, the flow of time could be completely different from what it is today. The heat death of the universe, a distant future when all stars have extinguished and entropy is maximized, might not be a uniform event for all observers. It is conceivable that some regions could reach this state rapidly, while others, protected by time-warping phenomena, could maintain a relatively normal passage of time long after the rest of the cosmos has fallen silent, creating isolated islands of time. What is even more extraordinary is that recent research points to time warping having a potential role in sculpting the universe's large-scale structure. The cosmic web, a vast network of galaxies interconnected by filaments of dark matter, might be partly a result of relativistic effects we are only just beginning to grasp. In the early, dense universe, the influence of time warping was significantly more powerful than it is today, suggesting it may have been a key architect of the cosmos we observe. In areas of greater density, the passage of time decelerated, a phenomenon that likely played a role in how matter aggregated and how the earliest stars and galaxies came to be. It's possible that the very architecture of our cosmos is a preserved fossil, an imprint of these ancient temporal distortions captured in the large-scale arrangement of all matter. This line of thought leads us directly to one of the most thrilling frontiers in contemporary physics, the meeting point of quantum mechanics and general relativity. When you zoom in to the most minuscule scales, quantum phenomena take over, suggesting that time's fundamental nature could be radically different from our macroscopic experience, with some hypotheses even proposing that it consists of indivisible, discrete packets. The consequences of a flexible timeline reach far beyond abstract physics, touching upon the core of what it is to be human within an endless cosmos. We find ourselves at an intellectual juncture, facing inquiries that were unimaginable only a century ago, such as how to find purpose when your entire reality is sculpted by forces you can barely grasp. These cease to be mere philosophical ponderings as we venture from Earth. They become critical, practical issues that will shape humanity's future. Because the universe is completely indifferent to our common sense, functioning instead by rules that are as elegant as they are foreign to us. Consider the immense solitude that time dilation could cause. If you were to journey to the closest star and return at a velocity approaching the speed of light, you might experience the passage of only a few months. Yet back on Earth, decades would have elapsed, and everyone you ever knew or cared for would be long gone, leaving you an orphan not of place, but of time itself. This profound displacement is the cost of challenging the universe's ultimate velocity, the consequence of engaging with the foundational principles that shape reality. Yet, within this isolation, a unique beauty emerges. You would serve as a living archive, holding the memory of a world that has vanished, a testament to a forgotten era. In a cosmos where time is relative, your memories become the sole anchor, and the experiences engraved in your mind would outlast even mountains and stars, making you a living monument to the fluidity of time. This concept points toward a future that feels incredible, yet is almost certainly unavoidable. As our civilization expands among the stars, humanity will fracture not just geographically, but chronologically. Separate colonies will live through history at varying speeds, giving rise to a sophisticated temporal web where concepts like past, present, and future are entirely subjective. A simple message between star systems would traverse not only space but also time, reaching a future its sender could hardly conceive. Children raised on relativistic starships would mature in a reality where time passes differently from their terrestrial ancestors, developing unique cultures and perspectives molded by their temporal circumstances, eventually leading to distinct branches of humanity divided by the very river of time. This splintering of timelines isn't a flaw in the universe's design. It is an inherent characteristic. The warping of time might be the cosmos's own method for guaranteeing that life and awareness can thrive on numerous timescales at once. Should a disaster eradicate one branch of our species, others would endure, safe within their distinct flows of time. In this way, we wouldn't simply be maintaining civilization across space. We would be creating chronological backups of it. Perhaps the most profound insight offered by time's flexibility concerns existence itself. You are not an external observer looking in on the universe. You are an integral piece of its architecture, threaded directly into the fabric of spacetime. This understanding casts us as the stewards of time in an otherwise inanimate cosmos. Your very consciousness, your perception of time's passage, might be the most precious phenomenon in existence, as it turns the cold mechanics of the universe into a vibrant, meaningful reality. In exploring this temporal maze, we've learned that reality is infinitely more bizarre and magnificent than we once thought. The malleability of time isn't merely a puzzle for physicists. It's a gateway to understanding the essence of being, revealing a universe that is less like a static machine and more like a dynamic organism, where time itself sways to the beat of matter and energy. So, when you next gaze up at the night sky, recall that you're witnessing not just faraway stars, but distinct moments in the cosmic river. A vast four-dimensional tapestry where each thread is a singular experience of time. And within your own private bubble of space-time, you are an active participant in this cosmic choreography. Your life, no matter how fleeting it feels, traces an indelible route through the very fabric of reality. You are more than a transient collection of matter. You are an everlasting feature of the universe's temporal map. Your own timeline, your unique perception of time's passage, possesses a reality and permanence equal to that of the stars themselves. The ultimate lesson you learn from time warping is this: you are not a passive victim of time, but its active co-creator. Every decision made, every path chosen, and every moment lived helps build the vast, intricate, and perpetually evolving architecture of space-time. You do not merely inhabit the universe. You participate in writing its ongoing story, instant by instant. The labyrinth of time extends infinitely in every direction, filled with wonders that defy your imagination and mysteries that have yet to be solved. But you are not lost within this maze. Instead, you are an explorer, a pioneer, charting the landscape of temporal understanding, pushing deeper into the very heart of reality itself. With each new step you take, you uncover different facets of the cosmic dance and discover new ways that time and space intertwine to form the rich tapestry of existence. Time warping demonstrates that the universe isn't just stranger than you imagine, it is stranger than you are capable of imagining. Yet it is also more beautiful, more elegant, and more profoundly interconnected than you ever dared to believe, placing you within something magnificent that transcends everyday experience and links you to the deepest structures of reality. Orbiting our planet is Gaia, a spacecraft that may hold the very keys to some of the cosmos's most perplexing puzzles. Launched in the year 2013 by the European Space Agency, Gaia is no ordinary telescope. It functions as a cosmic cartographer, diligently mapping the positions, distances, and movements of over 1 billion stars with an unprecedented level of precision. Imagine having the exact coordinates for 1 billion stars readily available to you. It is analogous to having Google Maps for the entire Milky Way galaxy, but with an astonishing degree of detail. One of Gaia's primary methods is parallax, an ancient technique given a modern application. By observing a star from 2 distinct points in its orbit, Gaia can triangulate its distance with extraordinary accuracy. But Gaia serves as more than just a cosmic surveyor. It is also a crucial tester of theories. You may remember those controversial hypotheses concerning gravity and dark matter. Gaia's data provides the means to subject these ideas to the most demanding scrutiny. Binary star systems, for example, are essential for testing theories like modified Newtonian dynamics, or MOND. Gaia's precise measurements of the positions and velocities of these stars could be what finally helps you determine which theory is correct. And the mission's scope is not limited to stars. Gaia also observes asteroids, planets, and even far-off galaxies, and its data have been instrumental in refining the Hubble constant, a key parameter that allows you to understand the expansion rate of the universe. Gaia's measurement of the Hubble constant has introduced a new complication to the ongoing cosmic debate, as different methods have produced slightly different values, making its data a vital piece of this immense puzzle. However, Gaia's mission is certainly not without its own set of challenges. While the spacecraft supplies a tremendous volume of data, the interpretation of that data is an entirely different undertaking. The very same information has been used to both support and discredit theories like cold dark matter and MOND, which has led to fierce debates within the scientific community. It is like gazing at a high-resolution photograph where every observer sees something different, either a flaw in the image or a revolutionary discovery. The final interpretation relies on complex statistical methods and, ultimately, on your most fundamental assumptions about the universe. There are few celestial phenomena as fascinating as binary stars. These are pairs of stars locked in a gravitational embrace, orbiting one another in a delicate balance between attraction and motion. As I mentioned before, these binary systems are not just spectacular sights. They are genuine cosmic laboratories where, through the intricate ballet of their orbits, you can test your deepest theories about the very nature of gravity. For centuries, binary stars have been a cornerstone of astronomical research. They have allowed you to measure the masses of stars, to understand their evolution, and even to confirm Einstein's general theory of relativity. Yet, in the context of the ongoing debate between cold dark matter and modified Newtonian dynamics, binary stars assume an even more critical role. The dynamics of their orbits can reveal whether conventional Newtonian gravity holds true, or if MOND actually provides a better explanation. Recent studies have plunged into this very question. Some, using data from the Gaia mission, have concluded that binary star systems behave exactly as Newtonian gravity predicts, which casts doubt on the validity of MOND. However, other studies present a different narrative, suggesting that MOND provides a better fit for some binary systems, especially those with wide separations between the stars and a weak gravitational pull. Could it be that both theories are partially right, or are you missing a crucial piece of the puzzle? The scientific community is sharply divided, and for good reason, because the stakes could not be higher. The behavior of these stars could either confirm our current understanding, or send you back to the drawing board in your quest to comprehend the cosmos. So, how can you effectively weigh the evidence? You can turn to Bayesian statistics, a mathematical framework that can tip the scales. Named after Thomas Bayes, an 18th-century statistician and theologian, it provides a formal way to update your beliefs as new data emerges, acting almost as a mathematical expression of the scientific method itself. The process involves starting with a prior belief, or your initial hypothesis, and then updating it as new data comes in to form a posterior hypothesis, which is a revised version that better aligns with the evidence. Within the context of these great cosmic debates, whether the truth lies with cold dark matter, MOND, or something else entirely, Bayesian statistics offers a rigorous method for assessing which theory is more probable given the observed data. For instance, these methods can help you quantitatively evaluate the likelihood that either modified Newtonian dynamics or Newtonian gravity is the correct theory when analyzing binary star systems. This is about much more than simply fitting a curve to data. It's about systematically evaluating the weight of the evidence itself, an approach that is useful far beyond the study of binary stars. From mapping dark matter in galactic clusters to calculating the expansion rate of the cosmos, Bayesian statistics have proven instrumental across a vast spectrum of cosmic inquiries. Yet, these methods are not universally accepted. The most contentious issue revolves around the selection of a prior belief, as the ambiguity in choosing an initial hypothesis without skewing the analysis can significantly shape the final conclusions. If your starting assumption heavily leans toward a particular theory, the final probability might appear to validate it, even when an alternative explanation is just as plausible. Despite grappling with such challenges, Bayesian statistics remain an indispensable part of our analytical toolkit, giving us a framework to interpret intricate spatial information, filter out interference, and isolate the essential signal. The universe, it seems, is unwilling to surrender its secrets easily, and as we accumulate more information, the argument over the fundamental nature of gravity only grows more intense. One astronomer recently captured headlines by stating, "It felt like I was dreaming," a sentiment born from the sheer surrealism of his findings, which failed to conform to any established results. His research has only added fuel to the fire, indicating that once the gravitational pull of stars in certain binary pairs drops beneath a particular point, their behavior aligns better with MOND models than with the standard gravitational model. The complication, however, is that his conclusions run counter to the findings of several earlier studies. He points out that while another team had been documenting an anomaly for a while, it didn't seem to correspond with the forecasts of current modified gravity theories. This conflict in the data isn't merely a minor inconsistency. It represents a foundational challenge to our entire conception of the universe. It forces us to question the dependability of our theoretical models and the very data we employ to validate them. So where does all this contradiction lead us? At the very least, it plunges us into a state of highly productive confusion, prompting scientists to conclude that cosmology itself, being built on general relativity, is in dire need of a major overhaul. The discussion is nowhere near finished. With every new piece of data and each refinement of our theories, the quest for the ultimate truth about cosmic gravity persists. In this pursuit, every anomaly and each conflicting result introduces a fresh layer of intricacy and awe, deepening the mystery we strive to solve. Within the field of cosmic discovery, the James Webb Space Telescope serves as a testament to human inventiveness and our unyielding curiosity. Its latest explorations into the far reaches of our own solar system have yielded discoveries that force us to rethink the potential for life beyond our planet. Among the host of celestial objects circling our solar system's giant, Jupiter, the moon Europa stands out as a world of exceptional interest, its fractured surface and concealed ocean having long captivated both scientists and enthusiasts. It is, however, the James Webb Space Telescope's most recent finding that has propelled Europa to the forefront of astrobiological inquiry. During an observation of the moon that was without precedent, the telescope identified the presence of carbon dioxide on its surface. While this might appear to be a simple chemical finding, its implications are truly profound, as carbon dioxide, a molecule vital to life as we understand it, could serve as a key indicator for life on other worlds. So let's examine the information supplied by the James Webb Space Telescope more closely. What mysteries does Europa conceal beneath its frozen exterior? And could this discovery of carbon dioxide truly be the clue that points to life beyond Earth? Shrouded in intrigue, Europa's landscape is at once captivating and alien, with an icy shell marked by a sophisticated web of lines and ridges. These formations, called lineae, are far more than superficial scars. They narrate a tale of powerful geological forces at work deep within. This icy crust, which is estimated to be between 14 and 24 kilometers thick, hides a tremendous ocean that has been a source of scientific fascination for many years. The lines crisscrossing Europa's surface are thought to be the product of the dynamic interplay between this icy shell and the Moon's hidden ocean, with cracks and ridges emerging as the ice shifts and fractures under the strain of its orbit around Jupiter. Beneath this frozen shield lies a saline ocean, with depth estimates ranging from 64 to 145 kilometers. This dark, cold, and hidden sea remains liquid not because of any warmth from the sun, but due to the colossal gravitational influence of Jupiter. A process known as tidal flexing, generated as the Moon travels around its giant planetary host, produces sufficient heat to keep the ocean from freezing solid. The chemical makeup of this vast subterranean ocean is a topic of fervent research and conjecture. Scientists believe that hydrothermal vents, much like those found on the ocean floors of Earth, may be active there. Such vents could supply the essential energy and mineral nutrients required to support life, positioning Europa's ocean as a leading candidate in our search for extraterrestrial organisms. Even the physical characteristics of Europa's ocean present fascinating possibilities. The existence of salts and the capacity to form complex organic molecules, when coupled with the energy from hydrothermal processes, foster an environment where life could theoretically emerge. Although the ocean's depths and pressures are extreme, they are not outside the known boundaries of habitability, as life in Earth's own deep-sea trenches has proven. Europa's enigmatic environment, with its icy face and buried ocean, already makes a powerful case for further investigation. But what precisely has focused scientific attention on this moon now? Using the James Webb Space Telescope, astronomers have made a compelling discovery. Through the analysis of data from NASA's Advanced Space Observatory, they have confirmed the existence of carbon dioxide on the moon's icy surface. This is more than just another entry in Europa's chemical inventory. It's a vital clue for assessing the moon's potential to harbor life. Employing a near-infrared spectrograph, the telescope was able to isolate carbon dioxide within a geologically young and turbulent area known as Terra Regio. This finding is significant not only for confirming the molecule's presence, but also for raising critical questions about its origins, which could point to a dynamic and potentially life-sustaining world beneath the ice. The carbon dioxide present on Europa's surface is thought to originate from its mysterious subsurface ocean, rather than being deposited by outside forces like meteorites. This realization points to a dynamic interchange between the moon's hidden ocean and its icy outer shell. What's most compelling is that carbon dioxide is not stable on the surface, which implies a constant replenishment from Europa's interior. Its detection in the youthful Terra Regio area suggests this is a recent and possibly continuous process that may hold the key to deciphering the ocean's chemistry and its potential to sustain life. So, what allows this celestial body to stay warm enough for a liquid ocean to exist, and what is compelling this gas to be released? The answer lies in a phenomenon known as tidal flexing, which results from Europa's gravitational dance with Jupiter. As Europa orbits the gas giant, Jupiter's immense gravitational pull constantly stretches and bends the moon, generating a significant amount of internal heat. This process is fundamentally different from the solar heating that warms our own planet, and it is this internal warmth that is believed to maintain Europa's ocean in a liquid state against the cold of deep space. The heat produced by tidal flexing could also be the engine for geological activity on Europa, such as subice volcanism and the formation of hydrothermal vents. Should these vents exist, they might be quite similar to those found in the deepest parts of Earth's oceans, which support vibrant ecosystems far from the reach of sunlight. The energy supplied by this constant gravitational squeezing could therefore be a critical component for life. On Earth, entire ecosystems thrive around hydrothermal vents, with life forms harnessing chemical energy released from our planet's interior, and a comparable process could be happening on Europa. Here, life could potentially harness energy from hydrothermal vents to power its metabolic functions, existing entirely without sunlight, by depending on the chemical and thermal energy from Europa's own internal dynamics. This brings us back to carbon dioxide, a molecule fundamental to life on Earth. Thanks to observations from the James Webb Space Telescope, which gave us detailed spectra of the surface, this familiar molecule now becomes a central figure in our discussions about extraterrestrial life. This powerful instrument allows astronomers to pinpoint specific chemicals, giving you a more complete picture of Europa's chemical landscape. On our world, carbon dioxide is a cornerstone of photosynthesis, the process that fuels most ecosystems. In the cold, alien seas of Europa, it might play a different but equally essential role in chemosynthesis, a process where life relies on chemical energy instead of light. On Earth's ocean floor, certain organisms combine carbon dioxide with hydrogen from hydrothermal vents to create organic matter. The carbon dioxide on Europa could be a sign that a similar process is underway there, which, naturally, leads to a fascinating question. Could the gas on the surface be a byproduct of biological activity in the ocean below? While purely speculative for now, this possibility adds an exhilarating layer to the search for life beyond Earth. To summarize, the potential for Europa to be habitable rests on three pillars: liquid water, energy sources, and essential chemical elements. The subsurface ocean covers the first requirement, and tidal flexing provides the energy. The detection of carbon dioxide now strongly suggests that crucial elements like carbon are also available, making Europa an even more compelling target in our cosmic search. This molecule could be a building block, a metabolic component, or a waste product of hypothetical life, but its presence confirms Europa is a chemically active world. As we enter a new chapter in astrobiology, the discoveries from the James Webb Space Telescope are fueling a future filled with incredible potential. Our exploration is set to expand dramatically with upcoming missions to Europa, including the European Space Agency's Jupiter 1CY Moons Explorer, known as JUICE, and NASA's Europa Clipper, both of which promise to deepen our knowledge of this enigmatic moon. The JUICE mission, which embarked on its journey on April 14, 2023, is designed to make thorough observations of Jupiter and 3 of its massive icy moons, with a special emphasis on Ganymede. Nevertheless, its flyby of Europa will yield crucial data that builds upon the James Webb Space Telescope's findings, giving us new insights into Europa's frozen crust and the ocean hidden beneath it. Following this, NASA's Europa Clipper is slated for launch in October 2024 and is engineered with the specific goal of studying Europa. Outfitted with an advanced array of instruments, this mission is tasked with performing a detailed survey of Europa's ice shell and its subsurface ocean, actively seeking evidence of habitability and conditions that might foster life. The overarching ambition of these missions is to advance the revolutionary discoveries made by the James Webb Space Telescope. By delving into the secrets of Europa's environment, meticulously examining its surface, and searching for biochemical traces, these endeavors will greatly improve our understanding of the Moon's capacity to harbor life, moving our quest from speculation toward tangible discovery. Beyond our solar system's asteroid belt and gas giants, there is a world that has long been wrapped in mystery. For many decades we have pictured Neptune, the eighth planet from our Sun, as a distant, deep blue sphere on the edge of our cosmic backyard. But I ask you to consider, what if this vision of that faraway world was merely a sophisticated illusion? This mysterious planet, which takes its name from the Roman god of the sea, has concealed its genuine appearance from us beneath a rich, blue veil. For decades, Neptune has been the focus of countless stories and scientific inquiries. However, recent revelations have pulled back its azure curtain, exposing a reality that is far more intricate and fascinating than we had ever conceived. For many years we have aimed our telescopes at this remote giant, capturing its essence through pixels and raw data. What we were seeing, however, wasn't the planet's actual appearance, but a reflection of our own technological and perceptual limits. The deep blue hue we came to associate with Neptune was the result of our own interpretations and image enhancements, a narrative we unknowingly authored and then came to accept as fact. Today, I invite you to see Neptune in a way you never have before, by exploring its true coloration, grasping the dynamics of its atmosphere, and untangling the mysteries of its moons and rings. For centuries, our depictions of Neptune showed a dark blue planet, a color that seemed to match its cold and remote position in the solar system. This view, which became deeply embedded in our collective imagination, formed a cornerstone of how we understood this ice giant. Yet, the history of Neptune's color is a tale of scientific progress and the relentless search for accuracy. It started with NASA's Voyager 2 probe, which departed in 1977 to explore the outer solar system. This spacecraft captured the very first close-up pictures of Neptune, presenting a world that appeared to be awash in a brilliant blue. These images, however, were not a pure glimpse of Neptune's actual color, but rather the product of data processing filtered through human perception and the technology of that era. The arrival of more sophisticated instruments, such as the Hubble Space Telescope and the Very Large Telescope, began to challenge this long-held story. Equipped with state-of-the-art technology, these observatories allowed astronomers to reassess the planet's true color, and their findings were nothing short of stunning. The new imagery showed that Neptune's color was not the intense blue we had grown accustomed to, but a far more subdued and varied palette, representing a profound shift in our comprehension of the planet. The reason behind this color discrepancy is found in the methods we use to process and interpret astronomical data. It's a common practice to enhance or alter colors in space imagery to accentuate certain features or make them easier for the human eye to distinguish. Over time, in Neptune's case, these enhancements cultivated the widespread perception of its deep blue appearance. So, what exactly prompted this revelation? The answer is found within a meticulous study titled Modeling the Seasonal Cycle of Uranus's Brightness and Color with Comparison to Neptune. This research, led by Patrick Irwin from the University of Oxford along with a team of specialists, initially set out to solve the puzzles of Uranus's seasonal light changes, but unintentionally ended up revealing Neptune's true colors and debunking a decades-old belief. To achieve this, The team conducted a painstaking analysis of an enormous dataset that spanned 6 decades, collected at the Lowell Observatory. This historical data, when combined with modern observations from the Hubble Space Telescope, allowed them to construct a detailed model of Uranus's average color and photometric brightness, exposing the complex dynamics of its seasonal shifts and the intricate relationship between methane concentrations and aerosol reflectivity. The intricate interplay of components within Uranus's atmosphere, shaped by methane ice particles, has introduced a new level of sophistication to our comprehension. A concurrent study provided a captivating point of comparison with Neptune, revealing that the variation in their blue shades is far less significant than commonly assumed. This insight emerged from a crucial re-evaluation of Neptune's coloration, effectively dispelling the deep cobalt image that has long been fixed in our collective consciousness. The team's approach combined quantitative analysis with atmospheric modeling and sophisticated spectroscopic observations to achieve this. They translated the measured reflectance spectra first into emission spectra, and then into tri-stimulus values, which effectively simulates how the human eye would register the planet's colors. This process, supported by instruments like the Hubble Space Telescope and the Very Large Telescope, enabled a re-examination of both planets' true colors with unparalleled precision. When you explore Neptune's mysteries more profoundly, you are plunged into a vortex of atmospheric chaos, a striking departure from the comparative tranquility of its neighbor, Uranus. Neptune's atmosphere is a turbulent and ever-changing environment, boasting the most severe weather conditions found anywhere in our solar system. Among the most remarkable aspects of Neptune's atmosphere are its gigantic storms, the most renowned being the Great Dark Spot, which the Voyager 2 spacecraft first detected in 1989. This enormous storm system, which brings to mind Jupiter's Great Red Spot, serves as powerful evidence of the planet's tumultuous character, and offers you a glimpse into its fierce atmospheric forces. Propelling these tempests are the most powerful winds in the entire solar system, with speeds surging as high as 2,100 kilometers per hour. Even now, the immense force and magnitude of these winds continue to mystify scientists, prompting questions about where they come from and what energy source sustains them. By comparison, neighboring Uranus presents a vision of serenity, as its atmosphere of hydrogen, helium, and methane does not feature the violent storms that define Neptune. A further perplexing feature of Neptune's atmosphere is the appearance of anomalous hotspots, where temperatures can climb to an astonishing 750 degrees Kelvin. This intense heat is a true paradox, with potential explanations pointing to internal mechanisms like auroras or magnetic events in its plasma layers. The genesis of these hotspots and Neptune's severe weather remains a topic of active investigation, compelling us to find new explanations for planetary atmospheres. Looking past this atmospheric turmoil, you encounter a system of cosmic balance, where moons and rings circle the ice giant. Your attention is immediately drawn to Triton, Neptune's biggest and most fascinating moon, a world governed by seasonal shifts and atmospheric puzzles. This distinctive moon, with its backward orbit, was the final solid body that the Voyager 2 probe examined on its landmark voyage into the outer solar system. This retrograde trajectory strongly implies that Triton was captured by Neptune's gravitational pull, setting it apart from other moons. Its surface, blanketed in nitrogen ice, is geologically youthful and dynamic, featuring dark marks that signal geysers spewing nitrogen gas. Triton's tenuous atmosphere fluctuates in density with the passing seasons, offering a compelling case study in alien weather patterns. As the moon's southern hemisphere progresses through its summer, a season that lasts over 40 years, the faint warmth from the sun causes the frozen surface layer of nitrogen, methane, and carbon monoxide to turn directly into gas, gradually making the icy atmosphere denser. Identifying carbon monoxide in Triton's atmosphere, in addition to confirming the presence of methane, represented a major leap forward in comprehending this moon. The existence of these gases, especially the concentration of carbon monoxide near the surface, is what drives the atmosphere and shapes its seasonal behavior, necessitating a complete overhaul of existing climatic models for Triton. Yet Triton does not travel in solitude. Neptune is attended by a cohort of lesser moons, each adding to our knowledge of this faraway world. As you shift your focus to Neptune's rings, you find another facet of the planet's enigmatic character. These faint rings, consisting of dust and icy fragments, are the debris from shattered moons, with their properties being directly connected to the planet's actual color and atmospheric activity. The delicate shade of Neptune's rings, shaped by how light scatters through its atmosphere, contributes a distinct element to the planet's visual character. In 2022, the James Webb Space Telescope delivered the most pristine images of these rings we have seen in 30 years. Captured with an unprecedented level of detail, these photographs have fundamentally altered our view of this far-off world. The most remarkable aspect of Webb's new imagery is the exceptional clarity of Neptune's rings, some of which are so faint and dusty that they had not been observed since the Voyager 2 spacecraft's historic flyby in 1989. With its superior capabilities, the Webb telescope has successfully brought these long hidden rings back into sharp focus, revealing a system of bright, narrow bands interspersed with more subtle, dusty rings. This was the first opportunity for scientists to observe these features in the infrared spectrum, which offers new knowledge about their composition and dynamics. The planet itself, along with its rings, has a unique makeup. Unlike the gas giants Jupiter and Saturn, Neptune is classified as an ice giant because it is rich in elements heavier than hydrogen and helium. This composition is also what gives Neptune its trademark blue appearance at visible wavelengths, a result of trace amounts of methane gas in its atmosphere. However, in the images from Webb's near-infrared camera, Neptune does not appear blue at all. Methane gas absorbs red and infrared light, yet instead of looking dark, the planet shows up as a brilliant, glowing sphere. This unexpected brightness occurs because high-altitude clouds of methane ice reflect sunlight before the gas below has a chance to absorb it, manifesting as luminous streaks and spots that give the planet an ethereal glow in the infrared. You might then ask why Neptune's moon Triton appears as a dazzling point of light surrounded by brilliant, glowing spikes, in sharp contrast to the planet's softer image. These features, known as diffraction spikes, are not physical objects, but are actually optical artifacts that result from the telescope's own design. As the light from Triton travels through the telescope's mirrors and structural supports, it diffracts, creating the prominent spikes that radiate from the moon. In simple terms, diffraction describes what happens when a wave, like a light wave, bends as it passes around an object's edge or through a tiny opening. Picture light behaving like water waves moving through a narrow gap in a barrier. Instead of continuing in a straight line, the waves fan out in various directions. This phenomenon of waves spreading out after navigating an obstacle is precisely what we call diffraction. The star-like spikes you see in the James Webb Space Telescope's images are a direct result of this effect, caused by the specific arrangement of the telescope's mirrors and supports. When light from a very bright source, such as a star or Neptune's moon Triton, enters the telescope, it bends slightly around these components. This bending causes the light to spread out, forming the distinct spiky patterns that are so characteristic of these images. Examining Neptune's rings, especially through the infrared spectrum, yields priceless information about the planet's atmospheric conditions and internal structure. The interplay between the rings and the atmosphere, particularly with the methane ice clouds, provides clues to Neptune's climatic processes. Moreover, a bright band encircling the planet's equator suggests the presence of a global atmospheric circulation pattern, which is the engine driving Neptune's powerful winds and storms. As our exploration of Neptune's mysterious realm draws to a close, it's important to consider how these findings influence the larger fields of planetary science and exoplanet studies. Once just a distant blue point of light, Neptune now stands as proof of the dynamic and constantly evolving journey of space exploration. The discoveries regarding its true color, atmospheric events, and the fine details of its rings and moons have significance that reaches far beyond our own solar system. These insights provide an essential benchmark for interpreting similar ice giants and exoplanets found in the far reaches of our galaxy, helping astronomers unravel the secrets of those distant worlds. As we continue to gaze out into the cosmos, Neptune serves as a powerful reminder of the infinite capacity for discovery, inspiring us to keep observing, keep inquiring, and keep solving the universe's puzzles. In the 21st century, humanity is at a pivotal moment in history, born in a time when we can observe the stars, but cannot yet travel to them. We find ourselves in an era caught between the complete exploration of our home planet and the potential to reach entirely new worlds. This is a journey not just of rocketry and physics, but one that is fundamentally about our survival and our ultimate place in the cosmos. Consider a future where Earth is threatened by an existential catastrophe, perhaps a massive asteroid, a total climate collapse, or some other danger we cannot yet imagine. In such a scenario, our hope might lie in generation ships. These would be enormous spacecraft, essentially mobile cities, where generations of humans would be born, live their lives, and pass away during a long voyage to another star, in search of a new home for humanity. We know from Einstein's special theory of relativity that traveling faster than light is not possible. And yet, this does not mean the stars are forever out of our reach. Even if we can only achieve a fraction of the speed of light, the vast expanse of space remains an attainable destination. Using advanced technologies like antimatter propulsion, compact fusion reactors, or even black hole engines, generation ships could travel the immense voids between stars at a substantial percentage of light speed. While this may sound like pure science fiction, it is a concept moving toward feasibility. These vessels would be far more than just transports. They would serve as humanity's lifeboats, engineered to support life for centuries, or possibly millennia, while navigating the perils of space, maintaining genetic diversity, and preserving mental well-being for all inhabitants. Each generation ship would function as a self-contained world, a miniature version of Earth, complete with its own unique social frameworks, cultural traditions, and the familiar routines of daily life. So, what would be involved in constructing such a vessel? And how could its population not only survive, but also flourish? Come with us as we explore the complexities of interstellar voyages that operate below the speed of light. Today we will try to unlock the secrets of how our species might one day travel to the stars, not in an instant, but over the course of many generations. Organizing a journey to another star system isn't merely a technological challenge. It also involves understanding the very reasons such a voyage might become unavoidable. There are plausible threats to our long-term survival that could compel us to find safety beyond our solar system. By examining these dangers, we can better prepare for future circumstances that might force humanity to undertake such a remarkable expedition. One of the most pressing dangers originates from space itself, as Earth's history is marked by asteroid and comet impacts that have triggered mass extinctions and drastic climatic changes. A sufficiently large impact event has the potential to make our planet uninhabitable, leaving us with no choice but to find a new world among the stars. Another grave danger is the possibility of a complete climate collapse. Human activities have already caused substantial alterations to our planet's climate, including rising global temperatures, the melting of polar ice, and increasingly violent weather. Should these trends continue unchecked, Earth could become inhospitable for human life, elevating the quest for a habitable exoplanet to our highest priority. Technological advancement, despite its enormous benefits, introduces its own set of considerable risks. Progress in fields like artificial intelligence, biotechnology, and autonomous robotics could give rise to situations where humanity is threatened by its own inventions. An out-of-control superintelligence or a weaponized pathogen could pose an existential threat, making the establishment of human outposts on other worlds a crucial strategy for safeguarding our species. In our search for a new planetary home, Proxima Centauri b emerges as a prime candidate. It is situated just 4.24 light-years from us in the Alpha Centauri system, making it the nearest known exoplanet located within its star's habitable zone. This region, often referred to as the Goldilocks zone, provides conditions where liquid water, an essential element for life as we understand it, could potentially exist on a planet's surface. Since its discovery in 2016, Proxima Centauri b has become a focus of intense scientific investigation. The planet orbits a red dwarf, which is a star both smaller and cooler than our Sun, requiring the planet to have a much tighter orbit to stay warm enough for life. While this proximity helps maintain a suitable temperature, it also exposes the planet to powerful solar flares and high levels of radiation, which are critical factors to assess before planning any human settlement. Current studies indicate that Proxima Centauri b has a mass comparable to Earth and is likely a rocky world. However, a great deal remains unknown, such as the exact composition of its atmosphere, or whether liquid water is truly present. To determine its suitability for colonization, future missions and more powerful telescopes will be essential to collect the necessary data before we could ever consider sending a crewed mission. The dream of venturing to the stars has always been constrained by the unyielding laws of physics and the immensity of time. Conventional ideas of space exploration, in which a single crew launches and arrives at their destination within their own lifetimes, appear increasingly unworkable when confronted with the vast distances between solar systems. It is here that the idea of the generation ship arises, a bold and creative answer to the puzzle of extremely long-duration spaceflight. Generation ships, which are also known as intergenerational or multi-generational vessels, are conceived to support human populations for hundreds or even thousands of years. These ships are designed as fully autonomous ecosystems, carrying not just the initial crew, but also all of their descendants. Life aboard a generation ship is intended to replicate a small, sustainable society, equipped with everything from living quarters and food cultivation to water recycling and complex social institutions. The underlying principle is straightforward but deeply significant. As the original explorers grow old and eventually pass away, their children, and then their grandchildren, will carry the mission forward. This continuous cycle of life ensures that the ship persists on its long voyage over many generations, with each new cohort being educated and trained to manage the vessel and, one day, to finally arrive at their new home. Such an approach to space travel demands extraordinary planning and highly reliable systems to guarantee the survival and well-being of the inhabitants. Every facet of existence must be meticulously planned, from maintaining sufficient genetic diversity for a healthy population to implementing cultural and educational initiatives that preserve and pass on essential knowledge and abilities. A major barrier to any form of faster-than-light travel is presented by Einstein's special theory of relativity. According to this fundamental theory, an object's mass increases as it gets closer to the speed of light, which in turn demands an exponentially greater amount of energy for any further acceleration. Based on our current comprehension of physics, traveling faster than light is effectively impossible. A workable solution that operates within the confines of Einstein's theory is the concept of generation ships. By embracing the long duration of the voyage and designing these vessels for multiple generations to live their entire lives aboard, humanity can realistically aim to journey to distant stars. This strategy not only accepts the constraints established by relativity, but also highlights the incredible adaptability and endurance of the human spirit. Reaching the stars means conquering immense challenges, chief among them being the vast distances that separate celestial objects. To make interstellar voyages achievable within a single human lifespan, we need to delve into sophisticated propulsion systems and the fascinating principle of relativistic time dilation. This effect is a direct outcome of Einstein's special theory of relativity and is crucial for long-distance space travel. As a vessel gets closer to the speed of light, time for those on board slows down in comparison to time experienced by an observer at rest. Consequently, for a starship moving at a substantial fraction of light speed, the crew's perceived travel time would be much shorter than for people remaining on Earth. For instance, if a spacecraft could sustain a speed of 90% of the speed of light, the effect of time dilation would mean that a single year for the crew would correspond to more than 2 years passing on our home planet. This phenomenon allows interstellar trips spanning many decades or centuries to feel significantly shorter for the travelers, although the actual distance covered remains unchanged. To attain the incredible speeds needed for such journeys, several advanced propulsion technologies have been theorized, each presenting a unique combination of benefits and difficulties. Antimatter propulsion, for example, would function by annihilating matter and its antimatter counterpart to unleash enormous quantities of energy. This process is vastly more efficient than chemical rockets, and could theoretically propel a spacecraft to a significant percentage of light speed, though the production and safe storage of antimatter present formidable technical barriers. Fusion propulsion represents another highly promising avenue for interstellar flight. A spacecraft could achieve powerful, sustained acceleration for long periods by harnessing nuclear fusion, the very same reaction that powers our sun. Engines based on this technology could generate the required thrust to approach relativistic speeds, transforming interstellar travel from a dream into a real possibility. However, mastering controlled fusion and adapting it for use in spacecraft propulsion systems continues to be a major engineering hurdle. A more speculative yet fascinating concept is the idea of a black hole engine. By tapping into the energy of a black hole, either through its accretion disk or via Hawking radiation, a vessel could in theory reach unbelievable velocities. Although this idea currently exists only in the domain of theoretical physics, it opens up some truly profound possibilities for the future of humanity's journey to the stars. Each of these propulsion concepts edges us closer to the dream of interstellar travel, making the vision of our species spreading throughout the galaxy feel increasingly attainable.